Okay, good afternoon, everyone. The topic of this session is shuttling through secret pipes, unveiling vulnerabilities in leading VPNs. The session focuses on vulnerability type in VPNs related to a mechanism known as name pipes. While you are familiar with using VPN, the concept of name pipes might be less known. This session will explain the name pipes in VPNs, and I will show how to implement them securely. I'm Zizi, a research engineer at Team T5 from Taiwan and a volunteer staff in HICON. I've participated in some CTF games with Belson team and have presented my research at several conferences. For the outline of this session, first, I'll introduce name pipes and the VPN vendors targeted in this session. Then I will provide the background of name pipes, explaining their functionality and how they work. After that, I'll discuss previous research, tools, and CV that are relevant to this topic. Next, I will dive into the methods I used in this research. I developed a tool to make analyzing the target more efficient. The main focus will then shift to the vulnerabilities I found in 3 VPN vendors. I'll explain how these issues were patched and offer insights on implementing more secure practices. Finally, I will share the timeline of reporting these vulnerabilities to the vendors and share some interesting experiences from the process. First, I'll introduce name pipes and the VPN vendors affected by the vulnerabilities. Name pipes were first introduced in Windows NT 3.1, released in 1993, and have been in use for over 20 years. They serve as a method for inter-process communication within the system. A name pipe is essentially a file object, and its usage is similar to file operations. We'll see this later. The management of name pipes is handled by a Windows component called NPFS, which means name pipe file system. With a basic understanding of name pipes, let me introduce the VPN vendor involved in this report. The first one is Windscribe. You may not be familiar with this VPN. However, I found their response to the vulnerabilities to be quite sincere. Windscribe is an open source VPN implemented in C, C++. My research into name pipe vulnerabilities in VPN actually began with Windscribe, which was the first vendor I chose to investigate. Next is CyberGhost. CyberGhost is a closed source VPN implemented in C#. I spent some time communicating with them during the vulnerability reporting. But in the end, the issue was marked as a duplicate. I will explain the details of the report later. OpenVPN is likely the one you are most familiar with. It's an open source VPN implemented in C. The vulnerability reporting was particularly interesting, as we had very active discussions. I will share more about that later. In summary, this research uncovered name pipe vulnerabilities in 3 VPN vendors. Both Windscribe and OpenVPN were assigned CVE. Unfortunately, CyberGhost considered it internally tested. In this session, I expect you will learn how name I will also introduce a unique feature of name pipes called impersonation. I'll explain how it's typically used by software and how attackers can exploit it, and the implementation for using impersonation securely. Before diving into the vulnerabilities, let's first cover some background information. The mechanism of name pipes is quite straightforward. Typically, there are 2 roles, the name pipe client and the name pipe server. These are usually separate processes, which makes inter-process communication work. The name pipe server processes uses the Windows API create name pipe, to create a name pipe, literally, we can specify the name of the pipe in the parameters. It then waits for a client to connect using connect name pipe. The name pipe client process connects to the server by using the Windows API create file, where the file name corresponds to the name pipe's name. Data is written to the other end using the Windows API write file, just like the file operations. The data is then read from name pipe server and using the Windows API read file, and it is similar in opposite. Finally, it closes the name pipe handle using close handle. This entire process is similar to file operations. As I said, name pipe is essentially a file object. Now, let's look at a unique feature of name pipes called impersonation, which works as follows. The name pipe client connects to the name pipe, and after a read operation, the name pipe server can then impersonate the client's process. This means the server can perform any action using the client's process security context, such as creating new processes. Since this mechanism can be used over the SAMBA protocol for remote connections across different systems, it is also often leveraged by attackers for lateral movement. In summary, name pipes provide a communication mechanism between processes and can be used remotely through SAMBA protocol. However, there are a few preconditions for using impersonation. When the name pipe client connects to the name pipe server using create file, the DW flags and attributes parameter should be at least security impersonation. So what exactly is security impersonation? It contrasts with 3 other impersonation levels. When the name pipe client connects to the name pipe server using create file, the impersonation levels are as follows. For security anonymous, the name pipe server cannot identify the name pipe client and cannot impersonate it. For security identification, the name pipe server can identify the name pipe client but cannot impersonate it. For security impersonation, the name pipe server can identify and impersonate the name pipe client, but this capability is limited to the same system. The last one is security delegation. The name pipe server can both identify and impersonate the name pipe client, and it also has the ability to perform remote impersonation. In addition to the limitations of the name pipe client, the name pipe server also requires the SE impersonate privilege when using the Windows API impersonate name pipe client. The following groups currently have SE impersonate privilege by default. This means if a process with this privilege or a user with this privilege is compromised, an attacker could gain access to it. Let's discuss the previous research, tools, and CVE related to this topic. I began researching name pipes after attending a talks by Lace and Ling at last year's HeCon. They were also focusing on name pipe vulnerabilities, but their target was Trend Micro's Apex 1. After listening to their session, I thought this attack surface seemed straightforward, so I decided to explore it further. When I first started learning, I found these tools helpful for analyzing name pipes. Pipe list from sysinternals can enumerate name pipes in the system. Access track from sysinternals can check the permissions of a name pipe, allowing us to see what permissions are required to read from or write to it. Process Explorer from sysinternals can retrieve the name pipe handles held by a process. And Wireshark can observe remote name pipe traffic over SAMBA protocol. My interest in researching VPN started after seeing the previous CVE in Windscribe. CVE 2018-11334 is a vulnerability which allows an attacker with any user privilege to exploit the Windscribe service namepipe for privilege elevation or denial of service. And CVE 2018-11479 is a vulnerability using command injection through the Windscribe service namepipe and lead to privilege elevation. Previous CyberGhost CVEs include CVE 2023-30237. It describes a DLL injection vulnerability, which initially confused me. How could DLL injection itself be a vulnerability? But after reading the next reference, I realized that the vulnerability actually involves using a namepipe to send a malicious JSON payload, leading to command injection and privilege elevation. So this raises a question: why is a command injection vulnerability labeled as a DLL injection vulnerability? And this answer relates to bypassing image checks, which is also why the vulnerability I found was marked as a duplicate. Lastly, let's talk about a previous OpenVPN vulnerability. It was featured in a Black Hat US talk of VPNX for 0 days leading to RCE, LPE, and KCE via BYOVD affecting millions of OpenVPN endpoints across the globe. It is a research presented by Microsoft researchers. In short, there are two vulnerabilities related to nampipes. CVE 2024-27459 could cause a buffer overflow, leading to a crash. And CVE 2024-24974 allowed a remote system to open an OpenVPN process. For details on how the Microsoft researchers turned these vulnerabilities into remote code execution, you can check out their bar. During this research, I created a small tool to improve the efficiency of my analysis. During the analysis, I encountered several challenges. If the code base of a software is large, how can we find the specific section of code that reads from or writes to the namepipe buffer? Setting breakpoints on read file and write file isn't effective because they are too similar to regular file operations, which makes it hard to distinguish namepipe operations. Secondly, if a software's namepipe server uses the Windows API get namepipe client process ID to verify the namepipe client, how can an attacker bypass this check quickly? Lastly, how can we test impersonation vulnerabilities automatically? Okay, there are 3 questions that I have to solve. So I created a tool called namepipe master. My tool includes the following functionalities. It can directly interact with the namepipes of the target process. It can inject a DLL into the target process to monitor namepipe operations. And it also uses a minifilter driver to monitor namepipe activities across the entire system. In actively interacting with the target process, namepipe master can actively connect as a namepipe client to other namepipe servers. On the contrary, it can also passively act as a namepipe server, waiting for connections from other namepipe clients. The third functionality is crucial and can be used to bypass image checks. It involves injecting a DLL into another process and then using that process as a namepipe client to connect to other namepipe servers. This also provides us a quick method to bypass image checks. By injecting a DLL into the target process, we can hook functions related to namepipes within the target process. By hooking NT create namepipe file, we can monitor the creation of namepipes. By hooking NT-create file, we can track NemPipe connection activities. By hooking NTFS control file, we can observe when a NemPipe is connected. By hooking NT-read file, we can monitor read operations from NemPipes. And by hooking NT-write file, we can track write operations to NemPipes. Additionally, we can bring the code stack in these hook functions, which makes analyzing the target more convenient. Since we can use the Windows API getFileType in the hook functions to confirm whether a file handle is a NemPipe handle. Furthermore, these hook functions allow us to test whether the target NemPipe handle can be impersonated. Finally, regarding the minifilter driver, it provides functionality similar to DLL injection, but with system-wide coverage, since it works at the kernel level. This allows for monitoring NemPipe operations across the entire system, not just within the process where the DLL is injected. In the minifilter driver, we can set up callbacks for IRP requests to gather the necessary information. We can monitor NemPipe creation in the IRP-MJ create NemPipe callback, and we can track NemPipe connection activities in the IRP-MJ connection in the IRP-MJ file system control callback. We can monitor read operations from NemPipes in the IRP-MJ read callback. We can also track write operations to NemPipes in the IRP-MJ write callback. By combining these three components, we achieve to analyze various NemPipe behaviors. And now, NemPipe Master is now open source. If you find it useful, please consider giving it a star. This tool is a free replacement for Pipe Monitor in IO Ninja without graphic user interface, but it can do more, like printing code stack by injecting DLL, testing impersonation capability, and interacting with NemPipe server and NemPipe client. We can use the tool to dynamically and deeply analyze a target with NemPipe. Now, we finally reached the main focus of this session, the 3 VPN vulnerabilities. Let's start with the vulnerabilities in Windscribe. A common type of NemPipe vulnerability involves a high-privilege service acting as the NemPipe server, which in this case is Windscribe service.exe, and a low-privilege process acting as the NemPipe client, here represented by Windscribe.exe. These two processes communicate through a NemPipe called Windscribe service. Using access check, the tool mentioned earlier, we can verify that the NemPipe access permissions allow any user, including guests, to read from and write to it. This means an attacker with any level of access can communicate with Windscribe service.exe through the NemPipe. As mentioned earlier, here's a part related to image checks. If the NemPipe server uses the Windows API get NemPipe client process ID to obtain the attacker's process ID when a client connects, and then checks the image path to verify whether the attacker's executable is signed with Windscribe's certificate. How to bypass the check? The answer has been told before. The answer has actually been covered earlier. To bypass the executable signature check, you can simply start your own instance of Windscribe.exe, then inject a DLL into it, and have this DLL establish a NemPipe connection within Windscribe service. This is why I automate this behavior with the tool I developed earlier. Manually writing and injecting a DLL for every exploit test would be time-consuming. As a NemPipe server, Windscribe service.exe receives commands from the NemPipe client and performs actions based on those commands. Since Windscribe service.exe is a high-privilege process, any action it performs after receiving a command are also run in high privilege. One of the commands is called command start WireGuard, which is a custom command defined by Windscribe. It takes parameters, exe name, and config file, which are intended to specify the WireGuard executable and configuration file. The namepipe client takes these two parameters using Boost archive library in C++ and sends them to the namepipe server. Let's see what issues arise from this operation. Here's the code where the vulnerability occurs. Can you find the issue? The first block simply appends .exe to the executable name. The second block combines Windscribe's path with the input exe name and config file to form a command. Finally, it executes this command using install service. So where's the issue? For those experienced with ZTF or bug bounty, this might be easy. By prefixing exe name, you can bypass the program's predefined path. So it is a path traversal vulnerability. This allows an attacker to use this vulnerability to install any high privilege service. We will demonstrate this vulnerability shortly. The second vulnerability involves another command, cmd taskkill, which also takes an exe name parameter. Yeah. Okay, let's continue. The second vulnerability involves another command, cmd taskkill, which also takes an exe name parameters. As the name suggests, this command is intended to terminate a process. This vulnerability is very straightforward. There is no need to bypass any check. The program simply uses taskkill to terminate the process specified by the exe name parameter. An attacker can exploit this vulnerability to use high privileges to terminate any process. This is a case of broken access control. The third vulnerability is in command add hosts, where the input parameter is hosts. From the name, it seems this function is intended to modify the hosts file. The host here refers to the etc host, which on Windows is located at Windows System 32 drivers etc hosts. This vulnerability is quite straightforward, as the attacker can control the host parameter, and the program will write it to the etc host. By modifying this file, the system can be tricked into resolving a domain to the IP address specified in the file. Therefore, an attacker can abuse this vulnerability to perform a domain poisoning attack. In short, this is a case of broken access control. Although we have discussed 3 vulnerabilities in Windscribe, today we'll focus on the privilege escalation vulnerability. The right side is Process Explorer. We can see Windscribe service.exe running in system privilege. And there is a low privilege process, Windscribe.exe. The CMD on the left top is also running in normal user privilege. We are going to exploit from this CMD. To exploit the vulnerability, we need to inject a malicious DLL into Windscribe.exe to bypass the image check and interact with NumPy server in Windscribe service.exe. After that, a malicious service will be installed running in system privilege. Now we can see a malicious service running in system privilege is pop up. That's the first demo. Thank you, thank you. Similar to Windscribe, CyberGhost has also a high privilege service, dashboard.service.exe, acting as the NumPy server, and a low privilege process, dashboard.exe, as the NumPy client. They communicate with each other using the NumPy CyberGhost service, using access track to see the permissions any user can read from and write to this NumPy. Again, similar to Windscribe, CyberGhost also performs an image check to verify whether the NumPy client's image path is on the whitelist. Therefore, attackers can similarly start their own instance of dashboard.exe and communicate with the NumPy server by injecting a DLL. I think my reports to CyberGhost are considered duplicate because of this bypass method. CyberGhost's NumPy communication method is the NumPy client sends commands, and the file NumPy server handles the command with high privilege. One of these commands is set PE launcher state, a custom command defined by CyberGhost. It takes a parameter called executable name, which is then serialized using JSON serializer library in C# and sent to the NumPy server. The program prepares to write to registry key under image file execution options by adding a subkey with an executable name and sets a value for the debugger within this subkey. The next time the system attempts to run a process with that executable name, it will execute the executable specified by the debugger instead. The vulnerability here lies in the fact that an attacker can control the executable name used for the subkey. Although the attacker cannot control the debugger value, they can still prevent the system from executing specific programs. It is this exploitation shortly. The second vulnerability is much easier and involves a command called lock internet connection, which doesn't require any parameters. As the name suggests, it can disconnect the system from the internet, allowing an attacker with low privileges to block the entire system's network access. And this is an issue of broken access control. Now, I will demonstrate the first vulnerability in CyberGhost that we just discussed. Dashboard service.exe from CyberGhost run in system privilege, and dashboard.exe run in normal user privilege. The CMD is also running in normal user privilege. We are going to exploit from this CMD. Open the registry editor. It has image file execution options, which the exploit targets. Similarly, to exploit the vulnerability, we need to inject a malicious DLL into dashboard.exe to bypass the image check and interact with NumPy server in dashboard service.exe. And you can see that a DLL is injected into the process. Now, we can see a subkey named cmd.exe under the key image file execution options. With the value debugger, while the data is not controllable, the executable name is hard-coded by CyberGhost with PE launcher state.exe. But it can still cause the system unable to PE launcher state.exe from CyberGhost is executed instead. So that's the second demo. Finally, for OpenVPN, there are several processes involved, but I will highlight two relevant ones. The process OVPN helper service.exe serves as the NemPipe server, while the OpenVPN connect.exe acts as the NemPipe client. They communicate with each other using the NemPipe OVPN helper service, using access track to see the NemPipe's access. Any user can read from and write to this NemPipe. Although this setup is similar to Windscribe and CyberGhost, the type of vulnerability is different. When the NemPipe client connects to the NemPipe server using create file, it sets security impersonation. Since the NemPipe server is running in high privilege, and thus it has SE impersonate privilege, it can impersonate the NemPipe client and perform actions with the client's permissions. This is how it works under normal circumstances. However, an attacker can fake the NemPipe server by creating a NemPipe with the same name as the OpenVPN service, tricking the OpenVPN NemPipe client into connecting to it. As long as the attacker has SE impersonate privilege, they can perform any actions with the OpenVPN NemPipe client's permissions. If this NemPipe client is also a part of the administrator group, the attacker can achieve privilege escalation. Now, let's demonstrate the privilege escalation vulnerability in OpenVPN. That's the last demo. OVPN helper service.exe and OpenVPN connect.exe from OpenVPN are running. The CMD is running as network service, which has SE impersonate privilege we need to impersonate the NemPipe client. We are going to exploit from this CMD. Okay, in this exploit, we create a NemPipe with the same name as OVPN helper service. And the NemPipe client will misconnect the NemPipe server, and the attacker can get the privilege from the NemPipe client. Therefore, the attacker can do anything under NemPipe client's security context. And that is the third demo. Once the vulnerability is patched, it becomes safe. However, the key takeaway is how it was fixed, as this will guide us in discovering new vulnerabilities and developing secure implementation. Learning from past solutions helps avoid repeating the same mistakes. The Windscribe vulnerability initially arose because we could control the exe name parameter to bypass the program's specified path and achieve privilege escalation. Now, it no longer allows us to specify parameters instead. It hard-codes the original two parameters directly. Since the original function was to execute WireGuard, it sets exe name to WireGuard service.exe and it sets config file to Windscribe wireguard.conf. Yes, that fixed the issue. A similar fix was applied to Windscribe's task kill command, which previously allowed specifying any exe name to terminate any process. Now, the command's functionality has been restricted to prevent arbitrary process termination. It directly hardcodes exe name to Windscribe OpenVPN.exe, and yes, which resolves the issue. The OpenVPN vulnerability originally allowed attackers to create a fake name pipe with the same name using a non-privileged process. This could trick the OpenVPN name pipe client into misconnecting, and it enables the attacker to impersonate it. To defend against this, the first step is to configure the access control list of the name pipe created by the OpenVPN service, ensuring that only high-privileged users can create a name pipe with the same name. However, there is still an issue. If the OpenVPN service crashes, or if an attacker creates a name pipe with the same name before the OpenVPN service does, what should be done? Therefore, an additional check mechanism is needed to verify that the process ID obtained from query service data for the OpenVPN matches the process ID retrieved from the one from get name pipe server process ID. Impersonation should only be allowed if these process ID are identical. The challenging part is over, so we can all relax a bit and enjoy the stories. In this research, I reported to 3 different vendors and had three distinct experiences. From Windscribe, I received both a CVE and bounty. From CyberGhost, I did not receive either. And from OpenVPN, I received a CVE but no bounty. In February, I reported the privilege escalation vulnerability to ZDI. In April, I reported the broken access control issue to Windscribe. And this led to an awkward situation where Windscribe quickly reviewed then fixed the vulnerabilities, including the privilege escalation issue. So it turned out that the related vulnerabilities should not have been reported to different parties. This case was reviewed by ZDI on April 30th. Unfortunately, it was also accepted by Windscribe on May 15th. ZDI reported an issue CVE 2024-6141 on June 20th. On the day of reporting to CyberGhost on April 19th, the issue was marked as a duplicate. It wasn't marked as a duplicate because the vulnerability I found was the same as others, but because CyberGhost believed that the vulnerability was due to the image check being bypassed by DLL injection. They intended to address the bypass method to fix the vulnerability. However, as far as I know, validating the namepipe client in a namepipe server is quite challenging. As of now, it seems the vulnerability hasn't been patched yet. Since it's not a high-risk issue, they might be taking their time to fix it. At the end of April, I reported the vulnerability to OpenVPN. A total of 7 people joined the discussion over time. From April 29th to May 9th, there are 44 email exchanges. Some of the solutions to prevent attackers from impersonating the namepipe server by creating a pipe with the same name were contributed by me. And I also help with code reviews. For example, I pointed out here is a memory leak and there's a handle leak. And yes, they fixed them very fast. Awesome. The issue was accepted and assigned CVE 2024-4877 internally on May 15th. And it is internally fixed on May 23rd. By coincidence, the vulnerability was published on the same day as Windscribe, and it has released the new version and the CVE. After this session, I hope everyone could understand the operation of name pipes and the mechanism of impersonation. We learned how to better analyze name pipes through API hooking with DLL injection and using a minifilter driver. And we get insights into the attack surface of name pipes by reviewing the vulnerabilities in the 3 VPNs, and we see how to implement name pipes more securely. Thank you to the 3 VPN vendors. All of the response times from these vendors were really fast, and they worked hard to fix the vulnerabilities I reported. Thank you to Angel Boy, Lace, and Kenny for listening to my research findings and providing valuable feedback. That's my sharing of this session. Thank you for listening. If you have any questions,